In this lesson, we're going to talk about natural base functions, which are all based on a number discovered by Leonhard Euler, a mathematician in the 1700s, that all stems from the following relationship. There's this number where if you take 1 plus 1 over n to the power n, and you plug in large enough n values, so as n goes to infinity, this number converges or gets really close to one specific number, and it's about 2.718, and I know a lot of these digits, 281828, and 4 or 5, I might as well show you the trick, 459045. I actually know this number out that many decimal places because I always remember, most people use just 2.7 for this number, but I remember the year 1828, and then a 4590, 45 triangle, and you can impress your mathematician friends with the fact that you know this special number, which is E. This is the natural base, E, and just like the letters I and pi, those symbols represent actual numbers. In this case, it's the same thing. So E, for us guys, E we're going to let be approximately 2.7, and most people know E is about 2.7, although of course it's an irrational number. This decimal place keeps on going on and on forever. There's, you know, those digits never stop, and that's just as far as I know. Now, this natural base E can be used to create functions, and you should be able to tell just by looking at a function. Let's say I have f of x. If it's exponential growth, it's going to be a times e to the power rx. And for it to be growth, just like before, remember that a value has to be bigger than 0 first of all. And for this to be growth, your r value has to be positive or bigger than 0. And then you're going to have an exponential growth function. However, if f of x is a times e to the rx, if it's decay, we got to have the a value once again bigger than 0, but now r has to be less than 0. If r is less than 0, this thing will be a decay function. So one of the first questions I could ask you would be in the following examples. In this example, we're going to determine whether the function is exponential growth, decay, or neither. So kind of like in the last section in 8.2, I like to write down the a value, and in this case it's a half, which is bigger than 0, which is a half, and that's bigger than 0. So far it's not going to be neither. If your a value is positive, it's either going to be growth or decay. What we need to look at for these natural base functions is the exponent, and that the number in front of x. That's like your r value. In this case, the r value is 3, which is positive. It's bigger than 0. So because the r value is positive and the a value is positive, this is going to be exponential growth. If you take a look at b, in this case, the a value is 2, which is bigger than 0, so it could be growth or decay. And r, the number in front of x, and the exponent is negative. It's negative 0.4, which is less than 0. That would indicate that this is going to be an exponential decay model. For c, my a value is negative 1. Right there, I could stop, because as soon as your a value is less than 0, it's neither growth or decay. So I'm just going to say neither. Another example that I can show you with e is simplifying with the base e. Guys, treat e just like you would any variable when you simplify. So for a, if I have 24e to the 8th over 8e to the 6th, I would say, alright, well 24 and 8, they're divisible. I can have that be 3. And then remember what you do with exponents when you divide like bases. You end up subtracting them, right? So it's going to be e to the 8 minus 6 power. So I'd have 3e to the 2nd power. And I would just leave it like that. That's the exact value. Let's look at this guy. I have 2e to negative 5x raised to the negative 2. There's a couple ways of doing this. One way is to distribute that exponent to both factors in the product. So I'd have 2 raised to the negative 2, and then e raised to the, now I have to multiply these two, right? And negative 2 times negative 5x would be a positive 10x. So I really have e to the 10x that stays in the numerator, and I'm going to bring this guy downstairs, making it 2 squared, and I can rewrite that as e to the 10x, and 2 squared is just 4. So I would simplify that expression to be the following if I don't have negative exponents. Something else you should be able to do is evaluate the natural base expression. What I mean by that is we need to actually use our calculators now to figure out, okay, what does this equal, or at least approximately, using our calculator. So what I'm going to do is the following. I'm going to bring up my calculator, and I'm just going to type in exactly what we see. So I'm going to put 3 halves, 3 divided by 2, and then it's times, and now there is an E button on your calculator, and it's, you have to hit the second and division button, and that brings up E, and then you can use the caret sign to raise it to any exponent you want, and if you hit enter, you'll get your approximate value. There is another place to get E, and I'll do this problem over again if I do 3 halves and then do times second, and then if you hit this ln button, which you don't know what that ln means, and you will this chapter, when you hit second ln, it brings up E and automatically gives you a place to write the exponent. So you can just type in 3. So that button, I like hitting second ln when I know I have to raise E to a power. And you get the same exact value. So let's go to just 2 decimal places. We're going to have about 30.13, right, if we actually wrote that. So this is about 30.13 if we evaluated that guy. Now let's do the next problem. If I have to do e to the negative 0.021 power, I would hit second ln, just because that brings up that exponent for me. I can do negative 0.021, close parentheses, and I get about 0.98 if we round to 2 decimal places. So I would say that this is approximately 0.98 there. Okay, so using your calculator is kind of easy as long as you know where to find the button. Okay, let's go on to the next slide. And if I cancel this out, alright, let's graph. So let's graph now with the natural base function. If we graph with our natural base function, we have the following generic function. A times e is our base, right? That's the natural base raised to the b times x minus h power plus k. Please keep in mind the parent function, once again, as always, just ignores h and k, which leaves you then with the following. Okay, it kind of helps at that point to note whether the function is going to be growth, decay, or neither, so you know you're graphing it correctly. And then just remember, you will want to shift accordingly. So I'm going to shift h units horizontally and k units vertically. Okay, so let's take a look at a couple of examples together. In example 4, we have the following graph. Negative 3 e to the power of 0.5x. Now notice this one doesn't have an h or a k value, or if you want to think of it, the h value is 0, the k value is 0, so we don't have to shift it at all. And because the a value is negative 3, this is neither growth or decay, right? This is neither. When we graph this, and I'll let you guys do this, only for graphing, I am okay to let e be approximately 3. Only for graphing, guys. Okay? Just because, you know, we're just kind of sketching a graph of what's going on here. If we wanted to be exact, we can use our calculator, and I'm fine with letting e be about 3. So, if we let e be about 3, we're sketching a graph of negative 3 times 3 to the 0.5x power. So if we were going to plug in some values, like 0, that would really be negative 3 times 3 to the 0 power, which means you just get negative 3 as an output. So if we were to plot that guy, you'll get that point right there. If we let x be 1, well, that would be negative 3 times 3 to the 0.5 times 1 power, which is just 0.5. So it's negative 3 times 3 to the 0.5, which we would need to use our calculator in order to figure out what e to the 0.5 is. And if you do, if I do negative 3 times 3 raised to the 0.5, you can check my work, but I believe you get about negative 5.2. Negative 5.2 if you type this into your calculator. So if we put that one down, that's going to be right about there. I'm going to plug in negative 1 and see what we get. If I plug in negative 1, that's going to be negative 3 times 3 to the negative 0.5 power. If you type this into your calculator, it's going to be negative 3 times 3 raised to the negative 0.5 power, and you get negative 1.73, or about negative 1.7. So negative 1, negative 1.7 is right about there. Now, this guy, since it's not shifted, the horizontal asymptote is still going to be the x-axis. We didn't shift that. And notice how these points are falling downwards. So I'm going to go like this, and it's going to keep on going. And as I move to the left, the graph is going to approach that horizontal asymptote. My domain is all reals. You can plug in any x value you please. Negatives, positives, zeros, okay. And the range, if you notice, all these y coordinates are under the x-axis, which means all these y outputs are less than 0, and you'll never quite get to 0 as you move to the left. The hardest type of natural base functions I can give you are like in part B, where you'll notice there is some shifting. But before I look at all that mess, I want to only look at that parent function, which, because we're graphing, I'm okay with letting e be about 3. So really I'm graphing 3 to the 0.4 x. Okay, so if we were doing this, and if I plugged in 0, I get about 3, right? Or excuse me, not 3. 3 to the 0 power would be 1, wouldn't it? So that would make more sense. If I plug in 1, it's going to be 3. So let's write that down. If I plug in 1, it's going to be 3 to the 0.4, which is about, let's use the calculator, 3 to the 0.4. It's about 1.56, or about 1.6, let's say. So 1.6. If we plugged in negative 1, that's going to be 3 to the negative 0.4. If you do 3 raised to the negative 0.4, you're going to get about 0.6. So 0.6 there. Let's plot those 3 points. 0, 1, 0, 1, hello, and then 1.6. And then negative 1.6 is going to be about there. Now, again, if we didn't look at anything else and we only look at that parent function, our a value is 1, which is bigger than 0, and my b value is also greater than 0, which means this is going to be growth. This is an exponential growth function, and that matches how my points are going. They're going upwards. However, I don't want to just stop my problem right now. We have to shift things around. My h value in this problem is negative 1, and my k value is negative 2. And hopefully by now you know that means move everything to the left 1 and down 2. So let's do that. If we move it, and maybe I'll use a different color for my final function, if I go to the left 1 and down 1, 2, I'm going to have that guy be about there. This guy to the left 1 and down 2 is right here, and this guy to the left 1 and down 2 will be right there. Now remember, the horizontal asymptote, which was the x-axis, also got shifted to the left 1 and down 2, which now puts it at y is negative 2. So we're going to start close to that asymptote and rise up through those coordinates up and away like so. Domain, all real, and the range, y value is greater than negative 2. And I believe all I would like you to try at this point is your self-quiz, which you have on your notes. Good luck with your quiz.